Today we're going to look at the confidence intervals for differences of means. So this is going to be very similar to what we did with differences of proportions. And while this isn't a joke, it's a great quote. Essentially, all models are wrong, but some are useful. So we'll be using a useful model to approximate the population for differences of means. We'll never get it exactly right, but it's pretty close. All right, so we're looking at resting pulse rates for a random sample of 26 smokers, and they had a mean of 80 beats per minute with a standard deviation of 5 beats per minute. Among 32 randomly chosen non-smokers, the mean and standard deviation were 74 beats per minute and 6 beats per minute. Both sets of data were roughly symmetric. Notice they're telling me some conditions here and had no outliers. So that's very important when we're doing this. Determine the 95% confidence interval for the difference in pulse rate for smokers and non-smokers. So what are we comparing? The mean heart rates for smokers and non-smokers, all right? Recall that we're going to use random variables again like we did on the difference of proportions. So to find the mean of the difference, we just subtract the mean for each of these samples. So our point estimate is going to be x bar 1 minus x bar 2. In this case, 80 minus 74, or 6 beats per minute. So that's our estimate for how far apart they are. But again, there's a variation, so this isn't exactly right. So there isn't only one possible value for the difference, so we have to consider the sampling distribution. When subtracting two independent random variables that have approximately normal distributions, the difference will also have an approximately normal distribution. So we just need to meet some conditions. The large normal, just like before, for the confidence intervals for means, where n is greater than or equal to 30 and the population is approximately normal. And the random condition, the data come from a well-designed random sample or randomized experiment. So if you say it comes from one of those things, that's fine. Or if they say the data is representative, that's fine. If we are not replacing, which is more for surveying than experiments, then we need to meet the 10% condition. Okay, so let's go ahead and check conditions. First of all, it's stated in the problem that the smokers and non-smokers were chosen randomly. So that's good. And they told us the data is roughly symmetric and has no outliers. So this condition is met. Now, let's go ahead and start doing, how does the calculation look? Well, we're still looking at the difference, and we're going to need a critical value t, and this is from your math chart. When we do the confidence interval, it's your statistic, plus or minus your critical value, times your standard deviation of your statistic. Remember, you can use 1var stats on your table of data to calculate your standard deviations for both samples. Degrees of freedom. Now, this is, again, this is a little different than before. It's still like the t interval. Well, this is a little different than before because we have two samples. So which one do we use? There's a conservative method where basically you calculate the degrees of freedom for each sample and use the smaller one. So you can do that if you need to show handwork. But honestly, most of the time when you're doing a t interval, you're going to be using the calculator, and it will do it for you. Just as before, if we need to do critical values, we're going to do 1 minus the confidence level because we're trying to find this z-score right here. And it's going to have a matching positive z-score over here. So I'm going to subtract this confidence level that I want from 1. And then I have to split the leftover in 2 to get this area. And if I do inverse t for that, that should give me the value. And then put in your degrees of freedom. Again, this is not on your math chart, so this is something you have to memorize going into your AP test. Standard error for the sample. So there's some slight changes here too. Basically, recall that if I have two independent variables, whether added or subtracted, I add their variances. So I get this. Because for each sample, it should be the population standard deviation by the square root of the sample size. You're going to square that, and that's going to end up with population standard deviation squared over sample size for both of them. We add them. And then to get back to my standard error, I'm going to have to take the square root of that. So that's what I'm going to be using. By the way, this is on your math chart on the back. Conclude is the same. We are X%, C% confident that the interval blank to blank captures, and remember, parameter and context. So if we're using the calculator to calculate a 2-SAMP-T interval using stats, we're going to press stat and then test. So we get to test, there's 2-SAMP-T int. Then we are going to select stats here, and X1 is the number of successes, standard deviation of your sample or standard error, and then your N1 is your sample size, and these are the same, they're corresponding. Then you're going to scroll down to, by the way, all these have to be integers. Then you scroll down and put in your confidence level in decimal form, and always select no unpooled. First of all, we didn't do pooled whenever we were doing confidence intervals before. We only did pooled when we did difference of proportions where the hypothesis was that they were the same. We'll talk some more about that with hypothesis tests for differences of means. Then you scroll to calculate and press enter, and it will spit your answers out. So looking at our example, by the way, this is the answers it spits out on this sample, but we're going to go ahead and go through the hand calculation just to show it to you. So there's my standard deviation or standard error calculation. Substituting my numbers, I get 1.44. I need my critical value. I'm going to use conservative degrees of freedom of 25 because the smaller of my two sample sets is the 26. And then I'll just do inverse norm of this with the 25 in it, and I'll say, oh, I'll use negative 2.06. Doing my point estimate, plus or minus my critical value times my standard error. This is the confidence interval I get. Now, why do I get a different one? Well, you can see the calculator is actually quite powerful. It's not a simple calculation. And it's getting a much higher confidence interval, which means it can be tighter. I mean, much higher degrees of freedom. So its confidence interval can be tighter. So yes, you have my permission to show, go ahead when you're doing this, I would go ahead and do the calculator and show what your DF is, all right? So our conclusion is we are 95% confident the average pulse rate for smokers is between 3.02 and 8.98 beats per minute higher than non-smokers. And there you go, and that's the confidence interval from the calculator. Now let's go ahead and look at a confidence interval using data. So it's very similar, scroll test, 2-SAMP-T int. This time you're choosing data. Make sure you have a list 1 and a list 2 for your data already. For frequency 1 and frequency 2, use 1 unless you actually do have a list of frequencies for your data, which should be pretty rare. Desired confidence level, in this case, 0.9%, 95% or 0.95. Pooled, always select no. Never jump into the pool, all right? And then calculate. So let's go ahead and look at how this is done for this. This is actually using this data we had here. So let's start with our state here, which is we want a 90% confidence interval for the difference of the mean fat content for the pizzas sold by the two national chains. And here's the data for each of the pizzas. And I picture a procedure as a 2-sample T interval. And first of all, is it random? There's no mention, actually. So we're going to just have to assume. So that's fine. Assume that the pizzas are representative. We don't know if it's random. And I'm going to check the large normal. This is not really more than 30, so I need to check the histograms. And sure, both distributions are roughly unimodal and symmetric. Remember, we're just trying to avoid strong skew and outliers. Now, I did adjust my windows on these because the range is so small. So I did an thing of 2. Sometimes your calculator will do an XCL of 1, and that'll make it seem like you have outliers or gaps. So do start to group them together a little bit to get a decent histogram. So let's go ahead and do the calculation. There are my data for my 1-var stats after putting these in the calculator. And here's my standard error. So my confidence interval, and by the way, I pretty much got this from doing the standard error on the calculator. So let's go ahead and show you how the confidence interval on the calculator. So I have my data already entered. and then we'll hit Stat, go to Test, 2SAMP int, almost there. Okay, now go there, press Enter, and I do see a minor error in here. So anyways, by the way, this is a 95% confidence interval. Ideally, you should change that to 90%. But you get the main idea here, all right? So there's all your data. It shows the interval, etc. Okay. Then we would write, and notice I even did it here. We are 95% confident that the average saturated fat content for brand B is between 2.73 and 6.71 grams higher than the average saturated fat content brand. If I had done a 90% confidence interval, this would have broadened a little. Okay, actually 90% would tighten it up because I'm making it a little bit smaller. All right. So it's tempting. By the way, one mistake I do see occasionally when we start this unit is people compare two separate confidence intervals and say, oh, well, I just did a confidence interval for pizza D and I did a confidence interval for pizza PJ, and they overlap. So there must be no difference. You can't do that. So I'm going to use this example here. I've got two diets with confidence interval, and I actually have the stats for it. So don't worry about it. The main point is I'm just trying to show you this effect. So I've got no statistical difference between these two diets. All right, Diet A and Diet B in terms of just looking at their confidence intervals compared to each other. So, but that rests on the assumption that the 2-pound difference is smaller than the sum of the two separate margins of error. So we need to sum variances instead. And when we do that, that changes things up. And we find out that we're actually going to get a smaller confidence interval of Diet A minus Diet B. And so for the data I used to generate these two, I also generated this interval. It doesn't include 0. And I'm going to go ahead and show you the calculator here going through this. So basically we have the data. We're going to do a 2SAMP int. Actually, I'm probably going to do 1SAMP interval for one of them. So you can see there's my data, my stats. I already had my stats entered in it. And when we calculate the interval, okay, go ahead. And we'll see if we're still, 95%. So there's my interval that matches this top one right here. Now I'm going to go ahead and do the 2SAMP int, pretty sure. Yes. And put in my data for those. By the way, this Diet B interval was generated the same way. So I have these two from the calculator when I calculated them separately. Now we're going to calculate them as a difference. And you'll see that, never jump in the pool. When we calculate that, this interval does not include 0. So there is a statistically significant difference between the two. And by the way, there's your degrees of freedom calculated on your calculator. So honestly, with 2SAMP ints, and when we get to these really crazy degrees of freedom, get to know your calculator, have it do most of the work for you.